This is an introduction to and worked example of the extended Euclidean algorithm, or the EEA for short, and a demonstration of its usage in computing the decryption key in RSA encryption. The EEA is used in the key generation phase of RSA encryption, which, if you're familiar with some of my other videos, you know is the process by which a key generator generates the values of P, Q, N, phi n, E, and D. The key generator will first generate two very large prime number values for P and Q, then generate their product N, generate the phi of N, which is equivalent to P minus 1 times Q minus 1, generate a value for E such that 1 is less than E is less than phi n, and E and phi n are coprime, meaning that they share no common factors other than 1. Finally computes D in the equation E times D mod phi n equals 1, plugging in the values of E and phi n and solving for D. The EEA addresses this very last component of key generation, namely how one goes about computing D in this equation. So I'm going to very quickly generate an example that we can work with here. I'm going to generate a value for P and Q equivalent to 53 and 61, respectively. I'm going to compute N as the product of those two prime numbers, 53 and 61. Get a resulting value of 3,233. The phi of N will then equal 53 minus 1 times 61 minus 1, which is equal to 52 times 60, which is equal to 3,120. Then I'm going to let E equal 7, because 1 is less than 7 is less than 3,120, and 7 and 3,120 share no common factors greater than 1. And then I'm going to say that 7D mod 3,120 is equal to 1. In previous videos, the way that I've approached computing D here is in a very, very intuitive, albeit somewhat inelegant manner. I said, okay, well I know that 3,121 mod 3,120 is equal to 1. So I've just said, why don't I set 7D equal to 3,121? I solve for D here, I get a value that is approximately equal to 445.857, which isn't going to work for our value of D since D needs to take on an integer value. So I've said, well, okay, this doesn't work. But I also know 3,120 times 2 plus 1 mod 3,120 is equal to 1. So I've set 7D equal to 3,120 times 2 plus 1 and get a value of D that is approximately equal to 891.571, which again doesn't work because it's not an integer value. So I try again with not a multiple of 2, but this time 3. So I set 7D is equal to 3,120 times 3 plus 1, and I get a value of D that is approximately equal to 1,337.286. And so I try one last time, this time multiplying 3,120 by 4. Setting 7D equal to 3,120 times 4 plus 1. And this time I get a value of D that is exactly equal to 1,783. And I finally have a valid integer value for d. This process is by no means a wrong way of computing d, and for small values of e, the EEA is probably pretty much comparable in terms of runtime to this more brute force approach. In the long term, though, if you want to work with bigger values of e, my approach is just going to take a much longer amount of time than using the EEA. So even though the EEA seems kind of unintuitive at first, it's worth having another tool in your arsenal as a key generator just in case computing d intuitively is taking too long. So now let's see how the EEA works instead. In this equation, ax plus by is equal to the GCD of a and b. EEA will compute x and y. And when we're using the EEA for RSA encryption, the coefficients a and b are substituted for e and phi n. So instead of ax plus by, we have ex plus phi n. Y is equal to the GCD of e and phi n. Now, since e is generated with the provision that e and phi n must share no common factors greater than 1, we know that the GCD of e and phi n, or the largest positive integer that divides both e and phi n, has to be 1. So then we have that ex plus phi n y is equal to 1. When we're finished executing the EEA, we can pretty much ignore this value of y that we get. It's the value of x in this equation that we're really interested in, since that value of x is going to be equivalent to the value of our decryption key d. To make this an example that we can actually work through, let's substitute in the values for e and phi n that we computed earlier. We have that e is equal to 7 and phi n is equal to 3,120. So we have 7x plus 3,120 y is equal to 1. We're going to first focus on the value of phi n, which in this case is 3,120. And we're going to see how we can express 3,120 in terms of e, which is 7 in this case. So I'm just going to say 3,120 divided by 7. And I'm just going to quickly execute this division. And I get that 7 goes into 3,120, a total of 445 times evenly, with a remainder of 5. I can then say that 3,120 is equal to 445 times 7 plus 5. Now I'm going to repeat this process, not for 7 and 3,120 this time, but for 7 and 5, my divisor and my remainder, respectively. And I'm going to see how many times my remainder goes into my divisor. So I'll erase this part on the left to have a bit more room. Let's see how many times 5 goes into 7. We have once with a remainder of 2. And I can say that 7 is equal to 1 times 5 plus 2. I'm now going to repeat this process once more for my divisor 5 and my remainder 2, and I'm going to see how many times that remainder 2 goes into my divisor 5. Once again, erasing over here. I'm going to say that 2 goes into 5 twice with a remainder of 1. So I can say that 5 is equal to 2 times 2 plus 1. And when you're doing this process yourself and you get a remainder of 1, That's your cue to stop. As soon as you get that remainder of 1, you're going to want to isolate it. So you say that 5 minus 2 times 2 is equal to 1. And so from here, from this equation, you're going to want to start substituting in values, namely values for your dividend and divisor, which in this case are 5 and 2 respectively. I'm going to first check where I got a remainder of 2. I can see that that's happening up here, where I have a remainder of 2 when I divided 7 by 5. I know that 7 is equal to 1 times 5 plus 2 is the same thing as saying that 7 minus 1 times 5 is equal to 2. So I'll write that over here just to make it really clear. And I'm going to substitute in 7 minus 1 times 5 in for 2 down here. So what I end up with is 5 minus 2 times 7 minus 1 times 5 is equal to 1. I'm going to do the same thing for the 2 5s that I have here. I'm going to check where above I've gotten a remainder of 5. And that looks like it's happening right here. And this equation is the same thing as saying 3,120 minus 445 times 7 is equal to 5. And I'm going to once again substitute in 3,120 minus 445 times 7 in for 5 down here, as well as over here. So I'm ultimately going to end up with 3,120 minus 445 times 7 minus 2 times 7 minus 1 times 3,120 minus 445 times 7, close parentheses again, is equal to 1. I'm just going to write this equation a little bit more neatly on the next page. Now I'm going to try to simplify this so that I get 7 times something plus 3,120 times something. So firstly, I'm going to multiply this 2 through and see if that helps. I'm going to have 3,120 minus 445 times 7 minus 2 times 7 plus 2 times 3,120 minus 445 times 7 is equal to 1. Then I'm going to multiply this 2 through to end up with 3,120 minus 445 times 7 minus 2 times 7 plus 2 times 3,120 minus 2 times 445 times 7 equals 1. I'll get rid of these parentheses. And I'm going to collect all the terms that contain 7 first of all. So I have negative 445 times 7 minus 2 times 7 minus 2 times 445 times 7. So these are all of my terms that contain 7, and then plus my terms that contain 3,120. So I have plus 2 times 3,120 plus 3,120 equals 1. I'm going to factor out a 7 here so that I get 7 times negative 445 minus 2 minus 2 times 445. And I'm going to factor out 3,120 here to get 2 plus 1 is equal to 1. I'm going to simplify the stuff in green to get negative 445 minus 2 minus 890, and negative 445 minus 2 minus 890 is just negative 1,337. Then I have plus 3,120 times 3 is equal to 1. And so I've succeeded in getting 7 times something plus 3,120 times something is equal to 1. And if you'll remember, the equation that we had was 7x plus 3,120y is equal to 1. And I said that the value of x is what we're really interested in. And so it looks like that value of x corresponds to negative 1,337. If you get a negative value like this, the last thing that you have to do to actually find d is take your value of phi n, which in our case is 3,120, and add that negative value to it. So you get a value of 1,783, which is the exact same result that we got when we used our first, more intuitive approach to computing d. So we're all set. If you're trying to work through an example of using the extended Euclidean algorithm, one thing that I found helpful is to just do your best to distribute constants that you see being multiplied against something in parentheses. So like up here, multiply 2 through, so like by 3,120 and by 445 times 7. Don't actually compute what 2 times 3,120 is, for instance. Just leave it in this sort of format. Resist the urge to write down the product right away. Another tip is to realize that you're ultimately trying to get a linear combination of e and phi n, so you have to do your best to try to isolate those values. The EEA is kind of tricky to get the hang of at first, and I have to admit that when I first learned about this approach for computing d, I thought it seemed a bit too overly cumbersome to really want to contend with, when it seems a lot simpler to just keep multiplying phi n by increasing values of some constant, add 1, and divide by e until you get a result for d that's an integer value. But the fact of the matter remains that when we're dealing with real RSA, sort of RSA that uses massive prime numbers and big values of e that are just impractical for didactic examples like this one, the EEA is going to be a lot more efficient than just trial and error, even if it doesn't necessarily seem like that in this example. Well, as always, I hope this was helpful. Thank you for listening, and stay safe out there.